All right. Okay, so power. So the Bell scale is just saying we take the logarithm base 10 of 2 powers. So this is a relative measurement. That's the other thing we have to keep in mind. There's always got to be a P1. So what is P1? Most of the time, 1 watt. Just to keep things simple, we just sort of define P1 as 1 watt, right? And so that means if I have, you got to think a little bit about how logarithms behave as well, right? If I have a power that's less than 1, right, my logarithms are going to be very, very small, right? And they're going to go negative. And if there's a logarithm, if it's greater than 1, it's going to get really, really big, right? I also can't take logarithms of negative numbers. So we're always talking about magnitudes, right? Magnitudes of powers, because that's the only thing I can take logarithms of, or you're going to get an error if you try to put it into Matlab, right? So I'm going to take P2 over P1, where normally P1 is 1 watt, but it doesn't have to be, right? If I needed, it's kind of like with voltage, right? It's a relative measurement. So I could say, well, how much more powerful is the signal at this point than this point? And I could say, well, if I input 5 watts and I get out 30 watts, I could find the logarithmic gain between those 2 points, right? And I could write it down in decibels or bells, right? So where does the deci come from? Well, it's just that a bell is so big, so we say it's a decibel. It's a tenth of a bell, right? So we multiply by 10, just to make it a little bit more manageable number, right? It's kind of like capacitance or charge, right? We're always talking about nanofarads because a farad is so big, right? Unless you talk about these new ultra capacitors and things. Dr. Lyon brought one into my office the other day, and it was like a 500 farad capacitor, and it was like this big. It's like, holy cow, right? I mean, it's impressive, but anyways, that's a different discussion. So we multiply by 10, that gives us the decibel. But when we're working with it, almost all the time, we see a 20. There's always a 20. And it's because we write down, not usually power, but the thing we're actually measuring, which is voltage. And so we typically are measuring an output voltage over an input voltage, right? That's what the transfer function was looking for. Well, so how does that give me a 20? Well, think about power. Power is IV, but it's also V squared over R, right? So if I have 1 power, P2, and that's V2 squared over R, and I'm comparing that to P1, right, which is V1 squared over R, and I take those ratios, right, P2 over P1 looks like the R's cancel out, and I get V squared, V2 squared over V1 squared. I can pull that out as a square. And then if I take the log, right, what do you do with the power of a log? It moves down as a coefficient. And then we have the 10 in there because of the decibel, right? And so that's why most of the time, this is the expression you're going to see for calculating the decibel scale of the magnitude of the output. It's 20 times the log of the ratio in voltages. Again, what's the V1? If we don't otherwise know, 1 volt, right? So if it isn't otherwise described, just assume it's a 1 to make your life easy, right? So now, when we're talking about transfer functions, we're going to typically be talking about the magnitude on a decibel scale. And so this is where we start to use something called a Bode plot to represent the response of our circuit. It gives us a graphical representation of the transfer function, right? Now, the book goes through, and it is kind of handy to be able to sketch a Bode plot by hand. Handy to sketch it by hand, huh? Okay. But if you can sketch it by hand, I mean, the main advantage to being able to do that is to get a quick idea when you look at an equation what the graph might look like. And honestly, right, if we have an equation that looks like this, and I ask you to tell me what it looks like, are you going to have any idea? I don't. Right? I couldn't look at that or any other random equation that you write down like that and tell you what it's going to look like, right? So I need to guide myself a little bit, right? And so if we break it down into its magnitude and its phase forms, it gets a little bit more manageable. And so I can look at the magnitude and I can find ways of figuring out how to plot this magnitude. So I can look at the magnitude in the decibel scale. And what, again, it allows me to do is if I can break my magnitude up into, well, like if we look at this one, well, here we have a square root on the bottom. But even so, typically if I were to look at the bottom, and if I could break that up, think about breaking this up into pieces that I could multiply together, if this got more complicated. We can use the power of logarithms to simplify our expressions. So what is the logarithm of a product? If I had log of AB, what does that become? How can we break that up? Yeah, Ravina?
Log A plus log B.
Yeah, I know. Everybody hated logarithms when you did them in your calculus class, right? It was probably the bane of your existence, trying to deal with logarithms. You're like, what the heck is this thing? Why do I need it? I don't like it. It just makes my life complicated. It was like complex numbers, right? Why do I need that stupid I? You know, who needs the square root of -1? It doesn't do me any good, right? Forget it. And you cleared your brain. And then all of a sudden now, you have to use it all the time. Guess what? That nasty logarithm that you also hate and was horrible, it is now your best friend, right? Just like complex numbers. And so it is helpful to remember some of those basic rules again. And things like that. Just like, you know, being able to move the power down as a coefficient, right? It lets us split up pretty complicated things, in fact, into pretty simple pieces. So instead of trying to take a log of a complicated product, where like if I had, imagine this being multiplied by something else that looked like it, that would be really disgusting. So instead, I can break it up, and if I could find nice little roots, I can split it up into addition, right? And I can just add those individual pieces together. And likewise, if it's taken to a power, a square, or a cube, I don't need to worry about that. I can just put the 3 down in the front as a coefficient. So it actually makes life quite a bit simpler. And we plot the function in its decibel form on a semilog plot, which means we have the horizontal axis in frequency, the omega, right, is a log scale. So if you look closely at this, notice here we started at 0.1, and then I move, here's say 1 block, right, 1 unit. So I go from close to 0 to 1, right? That's 1 unit. Now I go from 1 to 10, it's the same distance apart. And from 10 to 100, it's the same distance apart. So the horizontal axis is a log scale, where powers of 10 are uniformly spaced, right? The vertical axis is not a log scale, it's just a linear scale, right? So 0, 20, 40, 60, right, we'll go right up the scale. But the interesting thing is that the thing we're plotting on the vertical scale, which is linear, is actually a log, right? So the number we're plotting is a log, so we plot that number on a linear scale. But we want to see frequencies changing over a logarithmic scale, so we actually have to make the horizontal axis have that powers of 10 spacing. Right? And when we do that, it allows us to break up the individual pieces, and what you're seeing here, these red lines, are construction lines, they're called, by taking all these dashes, these dashed little dotted lines in here, These are all the pieces of the transfer function broken up like this. So if I have lots of pieces all multiplied together, when I take the log, I can add them instead. And so I can just draw a line representing each one of those individual pieces, and then add them together to get this resulting red line. And that resulting red line is the Bode plot. Then we smooth it out, we smooth the corners and things like that. There are rules for all of that. But this you can actually do by hand. And it's not very hard. It's a little annoying and it takes some practice, right? Which you'll get a little practice of. But you have some magic at your disposal. What do you have always available to you that would probably be able to plot a Bode plot for you? Multisim can do it. Yes, it can. And what else? Yeah, Matlab can plot Bode plots for you. Much better than you can draw them by hand, in fact, right? So, most of the time, I would recommend go to Matlab. Type your whatever equation you've got in, and have it take the Bode plot for you. And it's a command, Bode. That's it, right? So you put your transfer function in, and you spit out a Bode plot. We'll try, we don't have time to do it today, but I think next class I'll show you guys a problem in how you would actually input that into MATLAB. And it makes it a lot easier. But again, being able to follow the basic steps to plot the basic Bode plot is handy, just so that when you see an equation, you can immediately get a rough idea of which frequencies are important, whether it's going up or down or has bumps or things like that. We can do the same thing for the phase plot. We plot the phase on a Semilog plot as well. So the omega goes again in logarithmic powers, but the vertical axis here is phase, and it's maybe in this case it's in degrees. It could be a radians scale, but we aren't taking decibels of the phase. That doesn't really make any sense, right? Because we're talking about angles, and the angles just vary from 1 to 360, or positive to negative 90, or positive to negative 180. Right? And typically, that is also the scale we use. Most of the time with phase, you'll see it go, from negative 180 to positive 180, so that it's symmetric around 0, rather than like 0 to 360. Right? They typically do write it this way. In this case, it's just negative to positive 90 because that's just the range it takes, so they shrunk it down. But you can do the same thing. You get construction lines when you're looking at this expression for the arctan. You can build your lines, and there are some rules in the book that help you to figure out which direction it's going to go. And this is the table that's in your book. So when you look at your transfer function, and you have it in a magnitude and a phase form, if you factor your transfer function, right, split it up into little pieces that can be multiplied together. So again, like if I got a big polynomial, right, if I had, and again, you guys know I'm never good at writing down numbers that actually make any sense. Maybe I should go the other way. So if I had a transfer function, imagine it looks something like this. That's what I get out, right? I don't know what it came from. I just wrote it down, right? But that makes kind of sense. It looks sort of like the others. I'll tell you that this is, in fact, a very good transfer function. It's very, very well behaved, if you will. This would be like a stable system and everything, so because of where these locations of these roots are at the bottom. But right, this might have been multiplied out. If I were to have foiled this, I could see it as a big polynomial, right, a quadratic. And so that would be fine, right? If it were in that quadratic form, I would want to factor it to this. And then I would look at this and I would say, okay, this has a 1 over j omega plus 3 factor. I look on the table and I say, okay, where's something that looks like that? Oh, this one right here. That's a 1 plus j omega. And it's j omega over some number z, and it's a little small to read here. But if I were to take this factor then and divide by 3, right, I would pull the 3 out. So I would have a just a number multiplying the outside, constant, right? And I can look up a constant here. Right? The constant literally just raises me or lowers me. I just take the decimal version of that k, that number that's out front, 1/3 in this case, and I would put my line there. Then I would take this factor, this 1 over j omega 3 plus 1, I would look, that's this one right here where n is equal to 1, and I go along the line, if I were looking at my plot, I move along to this point 3. So I would find omega equals 3. I would draw a straight line to that point, and then, if this is actually I need to find the 1 over 1, which is this one right here. Right? So then from that 3, I would go down with a slope of 20 dB per decade. That is a number worth remembering. So the slope, that means if I started at, if I started here, whatever k gave me, if this was 20 decibels, and then this was near like the 0 line, then I would come down here, and at this point it would be a decade, which would mean if this is omega 3, this is omega 30. 1 decade means a power of 10 in omega, and we would be down to a 0 dB point. We would have gone down 20 decibels as we moved over 1 decade. And so you'll see that. That's the most common slope that's used. And again, this comes out because of that power of 2, this 20 log thing that happens in front, right? So this is the most common slope you'll find, and you would just draw that line. And then I would draw the line for this one, which would actually be at omega 2, and come to here, and then I would add those two together. And so, as you apply those, once you add them together, then you can kind of just start to sketch out what the overall graph is going to look like, right? Again, we're going to need to go through this in a little bit more detail, but so you can start to see and recognize as you look in the book, right? That's what this is talking about. And so again, it is handy to see how to do it, on a piece of paper. It may also be really worthwhile as you work on some of these homework problems. You can Google for Bode plot paper and just print it out, on a printer, and it'll give you those Semilog plots, and it'll give you a magnitude one with decibel scale and a phase one with angles. And if you want to practice doing some of these hand constructions, it's a lot easier if you have good graph paper, and you can just sketch along that. But again, we'll see how to do it in Matlab next week. And in most instances, I would encourage you to go to Matlab to do it. But again, conceptually, we want to understand where it's coming from. Okay? All right. So we'll talk more about the Bode plot next time, and then we will get into the concept of resonance.